start with questions from homework. So if you have something from 10-1 and that you wanted to talk about, now would be a good time to kind of do that. So that was like 1 through 40, I think, was what we assigned. Mary?
Number 18.
Sure. All right. So the directions here say to eliminate the parameter and then define or find the domain and range. So let's eliminate the parameter first. I'm going to take the equation for x and make that equal to t. So I'll multiply both sides by -3 to get that x is equal to -3x is equal to t. And then I'm going to go ahead and plug that in for t into the y equation. So when I square -3x, I get positive 9x squared. And positive 9 times -4 is -36. So there's eliminating the parameter. The domain comes from the x component. So I notice that the x component is a linear function. So the outputs of that linear function are going to be the domain for my function. So if my inputs are all real numbers, the outputs for a linear function should be also all real numbers. The range is going to come from the y component. Now the y equation is a quadratic. So the outputs from a quadratic equation are not going to be all real numbers. They're going to either go from -infinity up to the vertex or the vertex up to positive infinity, right? So which one do we have? Well, it depends on if the parabola is opening down or opening up. I can tell it's opening down because the leading coefficient is negative. So I just need to find that the output at the vertex, right? So I remember for the vertex, the x-coordinate is -b over 2a, which is 0. So when I plug 0 in for t, I get 3. So my range then should be -infinity to 3, and then I need a bracket on that because 3 is a possible output of this, right? When I plug 0 in, I actually get 3. Is that? Okay. And again, this is the key observation, is that the output for the y is fundamentally different because it's a quadratic as opposed to a linear. So we have to be really careful there. You feel good though now? Sure. Who else has some questions? If you have something from 10-1, 1 through 40, good time to ask. We have lots of time to deal with some questions if you have something. Okay, so it doesn't look like we have anybody else. If you change your mind, though, feel free to let me know. Happy to do more. Today, we're going to be looking at section 10.2 and talking about parametric motion. Any of you guys in physics in here? This should look familiar today then. Cool. So when we talk about like physics students, when we talk about kinematics or motion, we probably really talk about two different types of motion, right? One-dimensional motion, where something's just moving like up and down, and then two-dimensional motion, where it's like moving out and up, right? You know, like throwing a ball up and down, one-dimensional, versus like playing catch, two-dimensional. And I don't think we probably do 3D. Anybody does as a high schooler. That would be, I find that very surprising. So let's start with just one-dimensional motion here. So we'll define that. So in physics, we use the letter S as our position function. So in a one-dimensional motion, the height is the position. So we're using S to represent the height of our falling object. So the height S in feet and the vertical velocity V in feet per second of an object in free fall, ignoring air resistance, after t seconds are given by the equation S of t equals 1/2 gt squared plus v naught t plus s naught, or v of t equals gt plus v naught, where g is gravity, that's negative 32 feet per second squared. S naught and v naught are the height and velocity when the object's at time 0, basically the initial position and the initial velocity for our object. Let's do an example where we can apply this. Okay. So it says a ship is stranded in the ocean. On the top of the bridge, 80 feet above the water, a distress flare is shot straight up with an initial velocity of 72 feet per second. Provide a graph of the flare's height versus time and find the height of the flare above water after 1, 2, 4, and 5 seconds. So let's just sketch a little picture of what's going on. So we have some water. Here's my boat. There's like the top of my bridge. And then like I'm shooting a flare like straight up and down, right? So are we going to be using the position equation or the velocity equation for this? What is the question asking for? Heights, right? Height is position. So we're going to be using that equation there, or really simplify down when you plug the negative 32 in for gravity, that guy. So my V naught, the initial velocity, it tells me is 72. And the S naught, the initial height, is 80. So there's my one-dimensional function, or one-dimensional motion equation. So I'll go ahead and just turn my calculator back to function mode. do negative 16x squared plus 72x plus 80. We'll go and have to change our window now. So x here is representing time. I don't know how long that flare is going to be in the air. I'm going to guess, what, like 10 seconds or something is probably plenty. And I don't know how high it's going to go up, but it's starting already 80 feet above the ground. So maybe I'll go to like 0 to 200 or something. That seems pretty feasible. And then just let's hit graph and see what we get. Okay, so there's my time versus height equation. And if I want the height then at 1 second, I can just use my calculator. I can do second, trace, choose the value command, and to do 1. So the height there should be 136 feet. Second, trace, value command at 2 seconds, 160 feet, reaching its apex there, right? I don't think that's exactly the apex, but it's getting pretty close. Next is 4 seconds. So 112, we're heading back down, right? We're just a little bit, a little bit above that height that we started with. Second, trace, value, 5 seconds. And now we're at, height is at 40 feet. Now we're down below where we shot the flare from, right? Is everybody okay with the picture here? So notice I used function mode to do this. What if I wanted to write this as a parametric equation? How could I parameterize this? Thinking back to what we did in the last section, should be real easy. Is S of t a function? When we wrote it as a Cartesian equation, that's a function, right? So all we have to do is just make x of t t and y of t to be our function, and that'll give us should give us the same picture. So let's change that to parametric mode then. Get all that junk out of there. And we'll just graph this guy real quick and make sure that it's giving us about the same picture. Uh-oh. Missed a plus sign there. Okay. Go to my window. What did we do? We did like 10 seconds or something. X is the same as t, so I'll make that 0 to 10 also. Y, we did 0 to 2, so that looks good. If I hit graph, I got the exact same picture, right? Everybody's okay with that? Now, does that really describe the physical position of the actual motion of the flare? Does the flare go out and up? No, it's really just going straight up and down, right? So can I get my calculator to graph this so it actually just graphs the physical position of the flare? Sure we can. We need to use the parametric equation or parametric function like we're doing right now. So here, if I want x to represent the position of, or the horizontal position of the flare, what can I say about the horizontal position of the flare in the picture I've drawn here? Is it changing? No, right? It's not moving left or right at all, just staying straight up and down. So what should I change x of t to? A constant, yeah. Now I'm going to pick 1 instead of 0 because I don't want this to draw on the y-axis because I want to be able to see it. But like, yeah, any constant would be fine. So I can hit graph, and there it draws it. Now that wasn't very satisfying, right? All I have is this stupid little vertical line here. But what I can do that's even more fun is if I move my cursor over here next to the x of t, and I press enter, I can cycle through. Now I'm going to cycle to this one that's just like the oval looking shape here. If I hit graph now, watch what it does. So it just traces as it's drawing that graph, so you can actually see kind of like what the flare does in real time. Also worth using is if I pick the oval with the little tail on it, kind of looks like a key or something. This one will draw the line as it's moving. So it's going to draw the line as it's moving, but you'll see the motion. And then it draws the line as it goes, which is cool also. That's a nice function. And even from here now, I can do like second trace, and I can do value, and I'm just picking my values for t. So t equals 1. We're the same 136. I'm getting the exact same values that I did before. It's just now more of a realistic picture of like, what is that flare actually doing? So on these 1D problems, I can really use function mode or parametric mode. It doesn't really matter a ton. But I can't really model or graph the flare's actual behavior without parametric, right? All right. So let's talk now about like 2D motion. So here you're going to be having some horizontal motion as well as some vertical motion, like you're throwing a baseball or you're shooting a cannon or you're jumping over something, right? Where there's some vertical component and some horizontal component. So we say an object in projectile motion, that's two-dimensional motion, is projectile, with an initial angle of theta taken from the horizontal. What does that mean? So like say we have like some cannon and you know it shoots some little cannonball or something like that. Now let's actually draw it this way. So if I take this, that's what we mean by theta, right? You're just looking at the angle with respect to whatever the horizontal is at takeoff or at launch point or whatever. What can you say about these thetas? About the value of these thetas? They are angles. Yep. Where are they going to be between? What? Less than 1?
No. Between 90 and 180.
Does that angle that I drew between 90 and 180?
Below 90.
Yeah, they have to be acute angles between 0 and 90 degrees, right? If you fire it at exactly 90, it's just one-dimensional motion again. Just be straight up and down. Or if you fire it at 0 degrees, it'll be just, again, one-dimensional motion. It'll just be horizontal. unless you're firing like off a cliff or something, like straight ahead from an elevated position or something like a gun, or you're just shooting straight and then you have some drop from gravity. I guess you could do that. And that's technically projectile motion, I think. But that's more complicated because you're going pretty fast, and now you probably even have to factor the curvature of the Earth coming in.
But if you like, kind of off topic.
Yeah.
Like if you shoot a gun in space, there's no gravity, will it just keep going?
Well, there's no oxygen either, so you can't actually shoot a gun in space because there's no concussion. You can't actually form an explosion. So you can't actually do that.
What if you like threw a baseball in space? Would it just keep going forward?
You'd go backwards the same amount the baseball would go forwards. So that's physics for you. Like for each force, there's an equal and opposite reaction. The reason why you don't get that on Earth is because like your legs absorb that force.
So like, what if you're like standing on the moon?
Well, you could throw it really far. Your legs would still absorb the force.
Yeah.
If you're floating in the air,
It's like that.
yeah, there's still gravity, just not very much of it. John Paul? Sure.
Try it.
Okay.
Go to space.
Anyways, continuing on. And we have initial velocity v in feet per second, but we have to think about that velocity as a vector that has a horizontal component, the magnitude of v times cosine theta, and a horizontal or a vertical component, the magnitude of v times sine theta. So your x component is your x magnitude times t, and your y component is your negative 16t squared plus your y component of velocity times t plus your initial height. And then these are your velocity equations that kind of are the same idea. Mostly we use the position ones. All right, let's do some examples now. If you're on the baseball team or softball team, these will be really helpful to your game. All right, so you hit a baseball 3 feet above the ground with an initial speed of 135 feet per second at an angle of 16 degrees above the horizontal. Will the ball clear a 15-foot fence that is 300 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? So let's start by just kind of visualizing what's going on, right? So we'll write this as a parametric function. My x of t equation is the magnitude of the velocity times cosine theta. So that's 135 cosine 16 degrees t. And then y of t is negative 16t squared plus 135 sine 16t plus the initial height, which is 3. And again, I'm interested in positions, right? That's why I'm using the position version, not the velocity version, because it's asking like, where will the ball be? Right? Not any caring about how fast it's going. It's asking us about like, where's it going to be with regard to this wall? Above it, below it, whatever. Everybody's okay there? So let's take a look at our picture. So 135 cosine 16 times t. If you're graphing along with me, make sure that you put your calculator in degree mode. You're probably still in radian mode from last time, but certainly we need degrees here because we're talking about angles in degrees. So I got that. Set a window here. So baseball players in the room, 16 degrees like angle leaving the bat, how, like, what kind of hit is that? Is that like a pop fly? Is that like a line drive? What would you call that?
So it's like a line drive.
Seems line drivey to me too. How long does a line drive stay in the air?
Depends who hits it.
Depends who hits it. Okay. Let's say somebody competently strong hits it.
So it's like a second and a half. No, it's like 3 seconds.
Well, you're hitting it pretty hard. 135 feet per second is going like,
Yeah, so it's
you may be like Major League Baseball player strong to be hitting it that hard. Okay. Let's just pack on a little bit of extra on that. Let's make it 5, but 3's not a bad estimate.
Yeah.
I always like to, or 6, let's just double it, because there's no harm in going too much.
Yeah.
What you don't want to do is undershoot it. And then we'll set up our X-min. So the X is the horizontal distance. We care about this fence that's 300 feet away. So I'm going to make my X-min 0, but my X-max, I'm going to make like 400 or something, a little bit past that. And go by 50s or something, seems good. The Y's, so again, Y-min 0 makes sense to me. And if it's like a line drive, that usually doesn't get very high off the ground, right? So maybe I'll make that like 50 feet or something. You know? And that seems good to me. So let's hit graph and take a look at what we got here. So that's like my baseball. That's what it's doing. Everybody's cool there. Now what would be nice is if I was able to like put that fence in here somewhere so I can actually see where the ball is in regard or with respect to the fence. We can do that. I should have done this the other way. Let me just quick here move that down. I'll show you how to do that. Okay. So horizontally, where is the fence located? 300 feet away. That's constant, right? How high is the fence? 15 feet. But I also need the fence. If I just do 315, that's just going to graph a single point, right? I need it to graph all the points between 0 and 15 in between there, right? So what I'm going to do is I'm going to have this graph 15t divided by the t maximum. So what I'm going to do is I'm going to go and pick vars. The t max is a window setting, so I'm going to go under window. I'm going to go to the parametric and polar variables. And there's my t max. So let's think about what this does. T varies from like 0 to 6, right? So 6 is T max. I'll have like 0 divided by 6. That'll give me 0 or 300 comma 0. I have like 1 divided by 6. That'll give me like 300 or 1 over 6 times 15. So 300 comma whatever that is. And I'll keep going until I get to 6 over 6, which is just 15. So it's going to graph all the points whose x-coordinate is 300 with the y starting at 0 and going to 15. So that'll give me my fence. If I hit graph now, there's my fence. There's my baseball. Here, we'll do it the fun way, even. Oops. Okay, come on here. We'll use that one. Here's my fence. There's my baseball. Do we make it over the fence? No, right? Seems like it hits the fence there. So what we want to do is we want to find out now where the ball is hitting the fence at. Like how high up is it? Okay? So we're concerned about the position of the ball when its x is 300. right? So what I'm going to do is I'm going to use the x coordinate, or the x component, set that equal to 300, find the t, and then plug that into the y to figure out how high the ball is at that t. So this is very classic parametric function stuff, where you're going to be looking for one component or the other by just setting that one component equal to something, solving for t, then using that value of t in the other component. So to solve, 300 equals 135 cosine 16t. I'm just going to divide both sides by 135 cosine 16. If I type that into my calculator, I'm going to use the fraction command because I'd have to be kind of careful with my parentheses there in the denominator, and I just assume write it just like it looks. So I get 231-ish. So pretty good estimate being in the air for like 3 seconds, right? Somebody's played a lot of baseball. All right, and now what I'm going to do is I'm going to take that value and plug it in for y, or plug it into the y. So I can do this in my calculator. If I do vars, go to y vars, and this time pick parametric because I'm using the parametric equations. And I think I did put my position function in y2 of that number, enter. I have 3.51 feet. So we hit the fence 3.51 feet above the ground. 15. Not a home run, probably even catchable, right?
Yeah.
If you're standing in front of the fence, I would imagine you could catch a ball 3.5 feet above the ground. Assuming you can get there, but. All right. Let's look at another question. Okay. Similar setup. Jeff hits a baseball at 3.5 feet above the ground with initial speed of 141 feet per second at an angle of 24 degrees above the horizontal. Will the ball clear a 20-foot fence that is 400 feet away? If yes, by how many feet? If no, how high up the wall will the ball hit? Well, let's start by just writing our position equation. So same setup as before because it's really asking the same question, right? So 141 cosine 24t negative 16t squared plus 141 sine 24t plus 3.5. Let's go ahead and adjust our picture here. So that fence is now 400 feet away and 20 feet tall. Jeff hits the ball a little bit harder at a little bit higher angle, but not much harder, and doesn't hit it that much of a steeper angle. And I guess the ball's a little bit higher above the ground there to start. What do you think? Anybody with an intuition whether Jeff gets it or not?
No.
Let's take a look. Oh, I forgot to change the angles or the things here.
Am I hitting it out?
Yeah.
Let's make that 450.
You are. No doubt.
Let's make that like 100.
Middle. That's
100, yeah.
definitely.
Here's the hit. Oh, he made it. Jeff, you stud. All right. Yeah, I was like, watched the guy before him that didn't have a name. It's unfortunate he didn't have a name, but he's like, oh, little too steep. Or not steep, but, didn't get enough loft on that one. Got to hit it a little harder. Went up there and walloped it. All right, so we set up the same way. We take 400 and we set it equal to our x of t to solve for t. Let's see, what do we get there? So 311-ish. I'll then take that value for t and plug it in for y. Whoa, Boise. Did I just hear like a cat in the hallway or something? That was weird. Maybe it was freshmen.
Yeah.
Oh, wrong one.
Is that supercharger?
What?
So that was about 27.3 feet. Let's just do this. So we've cleared the fence by 7.3 feet. Jeff, you're the man. All right. Let's take the same circumstances. This is Jeff with his monster moonshot here. And we're going to ask, assuming that there's no obstructions, that the fence doesn't stop the ball, how far will the ball go before it hits the ground? So are we looking for a y or an x? An x. So we're going to be setting y of t equal to something, solving for t, and then plugging that t in for x. What value are we looking for of y? 0. How'd you know 0? Hits the ground. Excellent. So y of t was negative 16t squared plus 141 sine of 24t plus 3.5 equal to 0. How do we solve an equation like that? Quadratic formula. Yeah, there you go. Perfect. So the quadratic formula is negative b. So notice that 141 sine 24, all of that is b, plus or minus the square root of b squared. Notice that I'm putting that all in parentheses. If you don't do that, you're not going to get the right answer. Times 4ac divided by 2 times a. Okay. I'm going to do that all on my calculator. So second, y equals, give me that fraction command. Negative 141 sine 24 plus square root parenthesis 141 sine 24 parenthesis squared minus 4 times negative 16 times 3.5 divided by 2 times negative 16. So I get negative 0.06 seconds. That seems weird. Why? That doesn't make sense. What did we just find? We found like that end, right? That would be the height at time, or at height, or the time at height 0, which that's clearly not what we're looking for. What do we need to do then? No, man, we just go do the same thing. We just have to change it from plus to minus, right? Because it's plus or minus. We just must need the other answer. 3.64. That seems reasonable, right? The last one was 311 or something. So now we just do x of 3.64. So I'll just do that with the calculator. Vars, y vars, we're doing parametrics. I put the x component into x2t, so I'll pick that as number 3 of that answer. And we get 469.4 feet. Wozers. Good thing there's a fence. That'd be a long way to walk to go get that ball.
This year goes over the fence stuff.
True.
Yeah. So if you go over the fence, it's still not that far. Use the fence.
Well, not if you're playing, though. Like somebody else is going to go get that.
Yeah.
Right. If you're the outfielder, it's like that's a long way to run to go get the ball if it goes over your head.
Yeah.
Not counting the roll on it. Woof. I don't know how to do that. That's a lot of friction. It does depend on how long the grass is. All right. Let's do one more variation here on this. So assuming no other obstructions, what is the furthest distance away from the starting position that you could have placed that 20-foot fence and still have the baseball clear the fence? What are we looking for, an X or a Y? X. So we're going to start with Y of t. What's Y of t got to equal? Yeah, what's the minimum height the ball has to be to get the home run? Height of the fence, right? So it has to equal 20. So that's the equation we're going to be solving. Okay, how do I solve that equation? Not yet.
Factor.
No, not factor. What? Yeah, subtract the 20. It's got to equal 0 to use the quadratic formula. Not so fast. So we got that. So t is going to equal negative 141 sine 24 plus or minus square root quantity 141 sine 24 squared minus 4 times negative 16 times negative 16.5, all divided by 2 times negative 16. Here's the nice part about this. What's the only thing that's different from the way this is typed in from the last one? Just that, right? So all I'm going to do is go back and retrieve that last one and just go and change 3.5 to negative 16.5 and press enter. So 327, does that seem about reasonable to you guys? Yeah, that sounds good to me because it's in between the 364, that's how far the ball goes before it lands, and the 311, that's where it went over the fence when the fence was 400 feet away. So I got something in between those. I feel real good about that. Everybody's good? Okay. let's now plug that into y. I'm sorry, into x, and see what we get. Y vars function parametric x2 of that answer gives me 42107. So we can place that fence 421 feet away from home plate. He had 21 whole feet of clearance. That's pretty cool. What do you guys think? This is where I want to stop today. This felt like enough for one day, especially when you had 40 problems that you may or may not have gotten after yet. So for 312, the homework set now goes up to 48. That's this Sunday's. Next class, though, what haven't we done yet for this chapter? Homework quiz. I'd want to be familiar up to 48 in the event that there's a homework quiz next class. Again, does everything have to be done? No, but you need to know how to do the different types of problems, right? Like you have to know it good enough to where it's like, okay, I know what to do at least. Even if I make some little mistakes here along the way. Mr. Kulik's usually doesn't smash you up too bad for that kind of thing, but you do need to know what's going on, right? Mostly. Everybody feel good? Questions or anything? Okay. I'm going to stop here. I want you guys